So I hope everyone's doing all right and everybody's staying safe. It seems kind of silly to be doing this with everything that's going on, but uh, maybe it'll serve as a useful distraction if nothing else. I guess that's what we can hope for. Um, let's see. All right. So, in the discussions up to this point, we have been basically building up the structure of the field theory. We've talked about different sample systems. We've talked about the mean field approximation. Um, and today we're going to start going through one of the more useful analytical analyses that you can do with a field theory. Um, and that's kind of centers around the weak inhomogeneity expansion, where you basically come up with approximations or it's a kind of a more sophisticated analytic approximation to the field theory. And we're going to break this whole thing up into three parts. And the first one is going to be today, where we discuss the actual weak inhomogeneity expansion. Then what we're going to do over the next couple of lectures is then talk about one of the strategies for taking this and turning it into an expression for the free energy. If somebody has their mic on, can you please mute it? Um, unless you have a question, of course. All right, so to do this today, we're mostly going to be talking about just a really simple uh, homopolymer solution. For the most part, we'll talk about a dye block a little bit at the end. And I want to start by reminding us of two of the Fourier transform properties that we introduced in the first lecture, right? Because these are both going to be quite useful. The first one was the convolution theorem. So if we have f of r minus r prime, g of r prime, right, we know that this can be written as an inverse Fourier transform. So I use a really script f as the with the -1 to indicate an inverse Fourier transform, f hat of k, and g hat of k. And the other one that we're going to use is when we have an integral of the product of two functions, f of r, g of r. This can be written as the inverse Fourier transform. Oh no, I'm sorry, not inverse Fourier transform. This is just straight up the sum over k, f hat of k, g hat of minus k. All right. And so we're going to use these quite a bit going forward. This in combination with also the Fourier transform of a Gaussian. That's something that's going to show up a lot. And the main thing that we're going to be focusing on today is going to be on the molecular partition function of a polymer. That's really the key goal of that, is that the key goal of today is going to be to see what is the form of the weak inhomogeneity expansion, or in other words, what's the form of the resulting partition function when we assume that the fields are weakly fluctuating. All right, so we're going to start by going through this with the homopolymer, and we're going to go through a lot of it's basically just going to be a lot of gory derivation today. There's not going to be a whole lot of like physics insight, but there's enough subtlety in the derivation that it's worthwhile to go through it like kind of explicitly. Right, so we begin with the homopolymer partition function. So remember the way that we would write this. This is 1 over v integral dr to the n. And I'm also going to be, because eventually today we're going to be taking the large n limit, I'm also going to be quite loose with the distinction between n and n plus 1, because in the end, the 1 is not going to matter. And so then we have e to the minus. Remember, this was the Boltzmann weighted distribution of one of the n's, evaluated at the position of the end. Then we had the normalized bonding potential, right? So this is the Boltzmann factor of the bonds, but keep normalized so that it integrates to 1. Then e to the minus w of r n minus 1. And this continues all the way down to the last two monomers of the chain. All right. And so what we're going to do is make a really simple approximation. to the form for W of R, and then we're going to work out how that leads us to the final expression for Q once we simplify everything and truncate some of the higher order terms. So we're going to assume W of R is some mean field configuration that I'll just call W star that does not depend on R, plus epsilon of R, which is going to be a small spatially varying perturbation. Right? So W star, we're going to say is mean field solution. And then epsilon of R are spatially varying but small perturbations. And it's going to be defined in a way that the integral of the variations are zero. Right? So that's going to simplify a lot of our resulting equations. Okay, so if we imagine plugging this into our equation for the homopolymer partition function, a couple of things are going to happen. First of all, each one of these Boltzmann factors, so here, and all the way down to the last one, they're all going to give us an exponential of this constant W star. And so then that's just because it's not spatially varying, it's something that we can pull through the integrals, and we're going to have big N of them. And so they're all multiplied together. And so it just becomes e to the minus n W star as a prefactor. Right? So we'll have Q as e to the minus n W star as a prefactor. We still have our over volume. And then now all the Boltzmann factors in there have are going to carry just epsilon. E to the minus. And I'm also going to abbreviate my notation a little bit further. So I'm going to do this, and this is going to be assumed to be equal to of R subscript n. I'm just going to put the subscript directly on the epsilon. And then we still have the same thing for the phi variables. Right, so we have the bond transition probabilities. I'm just putting the R dependence and indicating that it's a subscript. Minus epsilon n minus 1, all the way down to phi 2, 1, e to the minus epsilon 1. All right. And now the next game is to just simply do a Taylor series expansion on all of the exponents, or all of the exponentials of the field, right? So since epsilon is small, it's reasonable to approximate it by a Taylor series. And so we're going to say Taylor expand e to the minus epsilon sub n. We're going to say that this is roughly 1 minus epsilon n plus 1/2 epsilon n squared. Then, of course, higher order terms that, for the sake of this, we're just going to ignore. And of course, a key thing that's going to happen from all of this is that any term after we do all this multiplying out that's linear in epsilon is going to cancel, or is going to drop out, because we defined above that it's going to be integrated over, when we integrate over all of space, that term should go away. So we multiply this out. Actually, wait, let me write out what this means. So before we start dropping terms, let me write this guy out. So I'll just write the first couple. So we have 1 minus epsilon n plus 1/2 epsilon squared minus epsilon n minus 1 plus 1/2. And then and so on along the chain. And now, we have n terms that have this form that are quadratic, and we have to imagine what we're going to get once we multiply all of that hot mess out. And so, of course, it's going to be kind of a complicated thing, but we're saved in some sense because all the linear terms in epsilon are going to be 0, right? So after multiplying out, right? So all of these can just be ignored or dropped because the integral of of epsilon of r is going to be 0. But we have to keep these linear terms, though, before we do the multiplying, because we are going to pick up terms that are epsilon n times epsilon n minus 1 from those. And so that's the thing that we have to keep track of. And so if we imagine multiplying this whole tedious thing out, all right, so now we're going to have q is equal to e to the minus n w star over v integral dr to the n. And then I'm going to, again, condense some of my notation. So I'm going to take all of those phi variables and just collect them into one big operator as a prefactor. Right, so this is, right, so this thing is phi n comma n minus 1 times phi n minus 1 n minus 2, and so on, all inside that big phi operator, just so that we don't have to keep writing them out. And then I'm just going to imagine what we would get if we imagine writing out all of these quadratic terms from above. And so first, the easiest thing to do is to sort of pick up all of the terms that are going to be quadratic in epsilon and involve epsilon sub n. Right? So we see one here that we know is epsilon n squared. So we have a 1/2. Well, first we have our 1, right? Because each one of these things has a prefactor of 1. So there will be one term that just gives us a unity. Then we have plus 1/2 epsilon n squared. The next term that involves epsilon n will be epsilon n that's negative up here and negative epsilon n minus 1 from here. And so the double negatives cancel. We get epsilon n times epsilon n minus 1. And then this is going to keep happening. So there's this ellipsis that's up here. It implies that there's a term like this that's epsilon that involves n minus 2 and all the way down along the backbone of the chain. And so this would keep going until we got to, so there would be a whole bunch of terms here plus epsilon n, epsilon 1, right? And so that's it for the epsilon n terms. And now we have to repeat all of that nonsense for epsilon n minus 1. So the next thing would be plus 1/2 epsilon n minus 1 squared, right? Because we still have the n minus 1 squared term. And again, that's going to keep going all the way along the backbone up to the end of the chain. And then, and the way the whole series is going to terminate, right? So there's going to be a whole other series of terms plus epsilon 2 epsilon 1. And then the final contribution will be 1/2 epsilon 1 squared. All right, and so I guess with this, I guess one thing that's important to realize is that we do still have a coordinate dependence. Like the place where the particle coordinates show up is in two places, right? And this phi, when we multiply it out, it's going to depend on Rn and Rn minus 1. And then Rn also shows up in all of the epsilons that show up with the subscript n, right? So this depends on Rn, this one depends on Rn, this one on Rn minus 1. And so we have those underlying particle coordinates that we have to be a little bit careful with as we think about treating this thing. And so we can rewrite this whole giant messy sum more compactly. So we have Q is e to the minus w star n over v integral dr to the n phi of r to the n. And then we have 1 from our prefactor of 1, and then the way that we're going to rewrite this is 1/2 sum from, use here m and j, m equals 1 to n, and sum j equals 1 to n. And I'll talk about this choice here in a moment. em, ej. All right, so when we did this multiplication out up above, right, we only had one term that was en n minus 1. And eventually what we're going to want to do is write this as a double integral. And To do that, it's easiest to start at one end of have our indices start at one end of the chain and go all the way to the other one. And so that's why it ends up being easier for us to have both of them go from m equals 1 to n and j equals 1 to n um, down the line. And you can see that this is still going to give us the right thing. So this is going to have two terms that would involve, say, for example, n and n minus 1. There would be one where m is equal to n, and there'd be a second one where j is equal to n. And the opposite one would be equal to n minus 1. But the prefactor of 1/2 is going to take care of that. But then there's only going to be one term where we have both of them equal to n, and so it gets its appropriate scaling of 1/2. Right, so everything should still work out as we expect it to. All right, and so now we can start reordering some things. So we get that this is now going to be equal to e to the minus w star n over v. And we can also take so we have this unity term here, and then we also have the sum term. And we're just going to go ahead and pass this integral through and evaluate it in both places. And in the first place where we just have the unity, when we take that integral, we're going to end up with just a constant of 1 for all of the bonds, except for the very last one that will give us a contribution of v. I'm happy to talk through that more if folks need to see that in more detail, but basically when we integrate this 1 times this phi of r to the n, it's just going to give us a factor of the volume. And then we still have all of this stuff over on the quadratic term, so this is going to be plus 1 over 2 sum over m, sum over j, dr to the n, all of our bonding potentials, and epsilon m, epsilon j. Sorry, don't need that comma there. All right. And then what I find is the easiest way to figure out how to solve this is to just kind of write it out for a really simple case with, like, I think what I've worked in my notes is n equals 5. So again, it's a little bit cumbersome to write it out, but it lets you sort of solve a non-trivial case. All right, so what we're going to do is examine n equals 5. And we're just going to focus on this term here when we go through this little sidebar. All right, so we'll have m equals 1 to 5, j equals 1 to 5. Integral, I'm going to write out the dr to the n, dr5, dr4, dr3, dr2, dr1, phi 4. So we have all of our bonding potentials. Right, so this is the thing that bonds all the monomers together. And then we still have our epsilon m, epsilon j. So it's still not at all trivial. And again, I think the easiest way to see how to go about writing down the solution to this is to just pick one of the pairs and evaluate the integral. And we'll be able to see a pattern that kind of emerges from doing this. So again, the pair that I've picked in my notes, I like to not start by picking chain ends because it will, they tend to give sort of end effects that I'd rather try to avoid. So let's pick one term. So we'll say that m equals 4 and j equals 2, right? So it'll be one monomer from the chain end and not adjacent to each other in the middle. Right, so in this case, what we have is dr5 all the way down to dr1, phi 5, 4, and I'm going to reorder things so that they're sort of in descending positions along the backbone of the chain. Epsilon 4, phi 4, 3, phi 3, 2, epsilon 2, and then phi 2, 1. All right, so all the terms that involve the monomers on the chain are kind of ordered. And then the way that I like to think about it is to just start at the way that I've written it, the far end of the chain, so where the index is equal to 1, and start trying to evaluate things. And so if we just pluck out from our integrals the integral over dr1, and we isolate all the terms that depend on r1, so then this whole thing becomes integral dr5 down to dr2 phi 5 4 epsilon 4 phi 4 3 3 2 epsilon 2, and then we have integral dr1 phi 2 1. Do have a comma there. So this guy, right, so let me write out the r dependence explicitly here. I want to rewrite this one so that it's r2 minus r1. Basically what this integral is saying is that we're, for some position r2, we're going to integrate over all space for the arbitrary position of r1, and we can easily do a change of variables here since r2 is effectively constant while we're doing this integral, so we can do a change of variables to r1 and just evaluate the integral, and this whole thing is just going to be equal to 1, right, because it's the normalized bond transition probability, and so it's not going to give us anything. And so for a fixed r2, right, so again, to think about this, we have a fixed r2, and we're integrating over r1. And so this is an easy case to do a change of variables where we can define, let me do it the other way. R2 dr12 is dr1. And because this is a Gaussian distribution, it's an even function, so the fact that I have the sign backwards doesn't matter. And so then when we do the integration, this whole thing just becomes 1. And by the same rationale, the exact same thing is going to play out when we start at the other end of the equation at monomer 5, right? So because this bond potential over here only depends on 5 minus 4, we can think about evaluating that integral over R5 with R4 fixed, right? So the same logic is going to apply there. Right, so then we have, so integral dr1 to phi of r12 equals 1, and so that term's gone. And similarly, we have integral dr 5 4 phi 5 4 also equal to 1, right? So that one's also gone. So what does this leave us with? Now we have, so we come down here, right? So it's the same thing, but now our integrals over 5 and 1 are gone. We have dr3, oh, sorry, dr4, dr3, dr2. And we still have epsilon 4. Make sure I get this right. Epsilon 4, phi 4, 3, phi 3, 2, epsilon 2. All right, and that's all we have left. So now, let me see, I want to rewrite this out with the integrals kind of explicit so that we can see what this is going to look like. So we'll have integral dr4 of epsilon 4, then integral dr3 of phi 4, 3. And then when we write the integral over r2, I want to write out the explicit dependency. So we have r3 minus r2, epsilon of r2. And so when we evaluate this thing, right, this is a convolution operation. The thing that we're going to get out of it is some function f1 that depends on r3, right? That's going to be the result of this operation because we're integrating out r2 and r3 is the other variable, so we're still going to have that. And because it's a convolution, well, let me see. So we can say that this is dr2 phi of r3 minus r2 epsilon of r2. And because it's a convolution, we know that we can write that as an inverse Fourier transform of the product of the two things. Right? So we have phi hat of k, epsilon hat of k. All right, so that's going to give us some f1 of r3. And so now we can rewrite this equation again with this new information. So this will be equal to integral dr4 epsilon 4 dr3 phi of r4 minus r3. But now I'm just going to write this as f1 of r3, right? Because that's all that's left. And again, we're basically in the same place. The variables are different, but it's still a convolution operation. And when we get to the result of it, we're still just going to have something that depends on only R4 now. So we can define F2 of R4 as the inverse Fourier transform of phi hat F1 hat. And of course, we know F1 hat is just the product of the first two. And so this is going to be inverse phi hat epsilon hat. All right, and finally we get just that this is now equal to integral dr4 epsilon 4 f2 of r4. All right, and then we can use the other Fourier transform rule that we started off with from today. Right, so we can use the other. Right, we know that we can write all of this as, we can write this whole thing as equal to 1 over v sum over wave vectors epsilon hat of k, right? And that's coming from the epsilon 4, then f2 hat of minus k. And now we can plug in for f2, and this becomes 1 over v sum over k. Right, f2 has a phi hat of minus k, phi hat of minus k, epsilon hat of k, epsilon hat of minus k. All right, and because remember, phi represents a Gaussian potential, and so this thing, phi hat of k, we know what this guy is. This is e to the minus k squared b squared over 6. And so this is, again, an even function, so it doesn't care if it's plus k or minus k. As long as it has the same magnitude, you'll get the same value. So we can use the fact that it's even, and we can write this then that all of this now becomes 1 over v sum over k. Now, where did it go? Phi hat of k squared epsilon hat of k epsilon hat of minus k. All right, so we've evaluated one of these cases in this sum. And so now, of course, there's what, I guess 5 squared minus 1 other ones to do, but fortunately the pattern, we can argue for the pattern from this pretty easily. So the thing that comes out is we see that we have this phi hat of k squared, right? And so this thing can be very easily analyzed. And remember that these phi hats, these are the bonding potentials that came about for the particles that were between the two places where we were evaluating the fields, M and J, right? So we wound up with all of the bonds between the two places where we were currently evaluating the field. They survived all this operation that we had been doing. And so, and we know that we can write this phi hat squared out as just simply e to the minus k squared b squared over 6. And so that's what one of them is. And then for the squared, we just pick up a multiplication factor of 2. And so remember, the specific case that we were solving was for m equals 4 and j equals 2, right? And so this is the number of bonds. So this is the number of bonds separating m and j on the chain. And so the general pattern that comes out is that each term is going to have the form it's going to be 1 over v sum over k, right, for some particular value of m and j, epsilon hat of k, epsilon hat of minus k, e to the minus k squared b squared over 6, and then absolute value of m minus j, right? So the number of bonds between m and j. And so now this is something that we can take all the way back up to q, to the partition function above, and we'll have our pattern. So now we have q is equal to e to the minus w star n over v, 1 plus 1 over 2v, then sum over m, sum over j, sum over k, then epsilon hat of k, epsilon hat of minus k, and then this exponential factor, k squared b squared over 6. I apologize for the lack of clarity in the difference between my b's and my 6's. If you ever need me to clarify it, don't hesitate to ask. M minus k. And we close our brackets. All right, so that's one of the big hurdles. The next big kind of hurdle of calculation that we have to go through is now going to be to evaluate these things, because I don't really like having these sums over m and j in here. And so this is where we're going to take the continuous Gaussian chain limit, and we're going to assume that we have a large number of monomers on our chain. And so we can replace these sums with integrals, and then we'll be able to get a nice clean closed expression. Although for a discrete Gaussian chain, this is already fine, right? This is basically the, this is the approximation that you would end up with. You just don't get quite as close form of a solution. All right, so now we're going to take the continuum limit. So we're going to take sum over m, sum over j, and those are going to become integral dm from 0 to n and integral dj 0 to n. All right, so again, we're assuming that n is large enough that we don't care about the distinction between starting at 1 or starting at 0. And so we're just going to give ourselves nice, clean boundary conditions. The only thing that's really a bit of a wrinkle in here that we have to... Wait, I have a mistake up here. I apologize. This should not be m minus k. Right? This should be m minus j. Right? It should be the indices, the number of bonds separating them. I apologize about that. All right, and so regardless, we can still take these sums and move them over to here and evaluate the integral on the right-hand side. The only thing that we have to be a little bit careful about is the fact that we have this absolute value in here. Means that we have to break the sum up into two parts, one where m is greater than j and the other one where j is greater than m. And then we have a pair of things that we can easily analytically solve. So we're going to have integral 0 to n dm, integral 0 to n dj, e to the minus k squared b squared over 6 m minus j. And so we're going to say that this is equal to integral 0 to m dm and integral 0 to m dj. Right, so this will give us half of this absolute value term, k squared b squared over 6. And then now m is greater than j, so we can write that absolute value as just simply m minus j. And then we have to tack on to this the alternative form where j is greater than m. So we have do j first from 0 to n, then dm 0 to j, e to the minus k squared b squared over 6. Then we just reverse the order, j minus m. All right. So we see this, and then, but the thing to realize here is that because we have, it's basically to within a change of variables, it's the same integral written twice. So we don't actually have to solve both of these pairs of integrals. We can just solve one of them and multiply by 2 because we're doing the same thing in both locations. Right? So it's the sum of two identical terms. Of course, you could solve them both and still get the same answer, but we're just going to throw a factor of 2 on. And so this is still then going to be equal to 2 integral dm 0 n integral j 0 to m e to the minus k squared b squared over 6, then m minus j with no absolute value to deal with. All right, and so now we just have like straight up integrals of exponentials, so this is really easy. Just grind through this real quick. First thing, I'm going to break the exponential up into a product of two things so that we can get the part over m out of the way. So I have minus k squared b squared over 6, and then times m times integral dj 0 to m e minus k squared b squared over 6 times minus j, so this becomes a plus j. And now we just evaluate the thing, right? So this is not hard at all. So we have 2 integrals 0 to n dm. So we evaluate the integral over j, we pick up a 6 over k squared b squared, and then multiplied by e to the k squared b squared by 6, and then j equals 0, and j equals m. Right, of course, when we evaluate it at the limit of 0, we're just going to pick up a constant of 1. That'll be floating around, and then, sorry, that needs a j up there. And then when we evaluate the other limit, we'll just get another factor of j equals m. All right, so this becomes, I can pull the constant prefactor out, so we'll have 2, 6 over k squared b squared. What are we going to have? Integral dm 0 to n. So at j equals m, we're going to have, so this is going to be multiplied by k squared b squared m over 6. And then at 0, it's going to be 1. So now when we multiply this exponential through, we'll get 1 minus e to the minus k squared b squared. All right. And now there's really nothing left to do except to kind of write down the final answer. So we end up with, so we do the integral over just the constant 1, and that'll just give us an n minus 0, obviously. Then we have another integral of the exponential that's subtracted off. We've already basically done a problem like, or done a situation like that, but still we can go ahead and run through it real quick. So we're going to have 2, 6 over k squared b squared, n minus 0 from the first one, and then plus 6 over k squared b squared, then exponential minus k squared b squared n over 6, evaluated at m equals 0 and m equals n. I have a sign error, I think. No, sorry, that was correct. The minus sign from the exponential kills the minus sign that's in the prefactor. All right. And so I'm going to pull this factor out all the way into the front, right? So that closes our brace, pull this guy out into the front. And since this one doesn't have the multiplication by 6 over kb squared, that's going to give us another factor there. So we're going to have 2 times 6 over k squared b squared, and all squared now because we're bringing that out to the front. And then we have n And now this is going to be multiplied by k squared b squared over 6. And then the result of the other term is that we have plus e to the minus k squared b squared n over 6 and minus 1. All right, and we see the same variable showing up over and over again, this combination of k squared b squared over 6, so we can just define the radius of gyration. So we use the definition of radius of gyration for a Gaussian chain, which is n b squared over 6. And the only place where we don't have it is in the prefactor. So out here, we're going to have to multiply and divide by n squared, right? So we multiply by 1 so that we can write this as in terms of RG. And so the whole thing becomes n squared 2 over k to the 4th RG to the 4th. Then we'll have k squared RG squared plus e to the minus k squared RG squared minus 1. Easy enough. And then this stuff is the thing that's commonly called the Debye function, right? So this is the Debye function. And so usually this this term is just going to be written as n squared g hat d of k. Oh, all right. So let's see, what else do we need to do here? All right, so we can just write down the kind of final form for Q. We'll get into using it a bit, not on Wednesday, but probably on Thursday. On Wednesday, I think we'll talk through like the basics of the structure of density functional theory that we're going to use to try to evaluate this guy. But we can go all the way back up to Q and write out the full version of Q, the full final version of Q. When we evaluate these things out to quadratic order, right? So we have Q is e to the minus w star n. I feel like I'm being really inconsistent with my use prefactors of volume here. I need to go back and clean that up, but and then we'll have, so everything that was to the right of the epsilon k, epsilon minus k is now just buried in this Debye function. So we have epsilon hat of k, epsilon hat of minus k, and then gd hat of k. And again, because everywhere inside the Debye function, k is raised to an even power, you know, it's an even function in the end, so it doesn't matter if it's plus k or minus k. All right, and so this is the full kind of quadratic approximation to the homopolymer partition function, written as a sum over the Fourier modes. We can also write the whole thing in real space. And so instead of writing this as a sum over Fourier modes, we can write it as an integral. And it's a little bit less straightforward than some of the integral rules that we've used before, because you can see that we have two functions multiplied together, which indicate with the same k that indicates a convolution. Then we also have a function of k times a function of minus k, so that indicates an integration over space. But what you end up with at the end is e to the minus w star n 1 plus n squared by 2v integral dr prime epsilon of r Debye function r minus r prime epsilon of r prime. I just got a question in the chat privately that asking about whether this first term should be 1 over v. I think this term is supposed to be a 1 here. I think I just messed up the factors of v above. And actually, I think the first expression that had the v's in it was correct, and then there was one in the middle that's wrong. I will mark up the notes and indicate where I think I messed up before I post these on the group website. All right, so this gives us the leading order fluctuation corrections to the mean field, to the homogeneous mean field approximation for Q for a homopolymer. we can still take this thing and take derivatives with respect to epsilon to get the deviations of the density, right? So you can still derive a density operator that includes first order corrections. Right, so the density operator. Right, this thing comes out to be like our rho tilde. This is minus n over q del q del w of r. It's going to have two contributions to it because w of r is going to have the homogeneous mean field contribution that gives you the average density. And then it's also going to have the fluctuation contribution that comes from this term that's up here. But in the end, what you end up with is rho tilde of r. And again, this is the sort of weak inhomogeneity approximation for it. This is the mean field term, right? This is the part that comes from w star, which is probably intuitive. And then the term that comes from over here, where you're just taking normal variational derivative stuff, right? So it's the convolution of the field with the Debye function. All right, so that's most of what I wanted to get through today. I have some notes here on what, just sort of a sketch of what is going to change when you do this for a dye block instead of a homopolymer. So I'm going to go through outlining that. We won't use it in the future lectures, but and I'm not going to go through in nearly as much gory detail as I did here, but I'll just kind of highlight the changes that take place when you start trying to do the same analysis for dye blocks. Right, so for dye blocks, again, let's define the problem. So we have, I always like to start with the discrete Gaussian chain sketch of things. So we'll have in B blue monomers and in A other monomers. And we're going to assume that all the bonds are identical. And we're going to define our F as the fraction of A, right? And N here, again, inconsistent with what I did before, we're going to ignore the difference between N and N plus 1. And really the key difference here is that now the field W is going to depend on the index. It's going to depend on where we are on the chain, right? So the key difference is that A and B experience different fields. So that makes the indexing, a bit more tedious to deal with. And so we're going to have our WA of R. This is going to be WA star plus epsilon A star of R, and WB of R is going to be WB star plus epsilon B star of R. All right, and so everything that we talked about above basically proceeds the same way, except that quadratic term, the thing that we kind of slowly took apart to be able to solve it, is now going to depend on the fields. Right, so the quadratic term changes. Quadratic term changes. And the key thing that changes is that we have sum from m equals 0 to n, sum j equals 0 to n, and epsilon hat of k. This now depends on m. It depends on where we are on the chain. Then e to the minus k squared b squared over 6 and minus j. Right, and so the kind of tedious and annoying thing that we have to deal with are the possible cases that can arise from this sum. So we will have terms where we have where both monomers involved in this calculation are A monomers. We'll have the case where both monomers involved are B monomers, and then we'll also have the cross term where we have A times B. And so what you end up with is there are now 3 contributions. Right, so if we just write this thing out, it would be equal to 2 sum m equals 1 and A. Actually, sorry, I'm going to write that out in just a moment. Sorry, and A. So this is the case where we have only A monomers involved of K, of minus K, then e to the minus K squared, B squared over 6, and minus J. And all right, let me see. Then plus, same thing. So now we have the B terms. So we'll say this is an A plus 1 to N. Actually, I'm just not gonna, again, not care about the puny little constant like 1. And A to N. All right, so this will be the B block. And then we have the cross terms. So we'll have plus. And actually, let me go ahead and just do this real quick. So one of the things that I wanted to change here is I want to make this, when we did the integrals above, we saw that it turned into a sum of two different integrals. And so, or two identical integrals. And the way that we got there was by making this just a parentheses instead of an absolute value. And then we changed the upper limit of this, right? And then we have a 2 in front. So I'm going to play the same game here. So this one will, again, only go to M, and then that becomes a parentheses. And then the last one, I'm just going to go ahead and write it out as though we've already done that. J minus M is the greater one there. Okay, and so this is basically at the point where we had it last time. And so now it's really straightforward to just take the sums to integrals. It's just a bunch of integrals of exponentials. It's not terribly difficult. So I'm just going to write down the final form of the solution. So we just integrate and collect terms. And what you should hopefully get at the end, after you, do the continuous Gaussian chain limit and all that fun stuff, minus WA star times N times F e to the minus WB star N times 1 minus F. All right, so there's a hot mess of equations, and then I have to define some things. So bear with me for a moment. This is minus 1 over N squared over 2V, sum over K, epsilon hat A of K, epsilon hat A of minus K. And then I will define this guy momentarily. So this is basically going to be a modified Debye function. And so I'm still using a subscript D to, but it now depends on two variables, F and K. And you see all of this stuff should be inside the sum over wave vectors. So we have plus 2GAB. And again, this is another funny little Debye function that I'll define. F of K is the cross term. Wait, this is B minus K. And then the BB term. So this one we can write as 1 minus F K and close the big parentheses and close the brace. Okay, so it's not short, but you can see the general expression. All right, it's your modified Debye function, so GD of F and K or 1 minus f if you're on the b block. This is 1 over k to the fourth rg to the fourth. And again, everywhere where you have an f, you would just put a 1 minus f for the second place where it shows up, and the cross term GAB hat of f and k. This one's a little bit different, so it's 1 over k to the fourth rg to the fourth. All right, and that's it. And again, you can get density operators by taking derivatives with respect to the a part or the b part from q above, and all those things kind of work out just like you'd expect them to. Or well, maybe you wouldn't expect it to naively, but with a little experience, you might expect it to. All right, so that's everything I wanted to get through today. If there are any last minute questions or anything, don't hesitate to ask. Otherwise, I will slowly start shutting this down and let this thing process, and I will upload the video and the notes as soon as it's done processing. All right, so stay safe, everyone.